Hello, everybody, and welcome to Astronomy on Tap State College. This is our 47th event. I've lost track of how many we've done virtual now, but welcome. If this is your first time, if this is not your first time, welcome back. Tonight's theme will be scientific controversies in astronomy. So we'll be talking about some interesting scientific discoveries in recent years and further back than that that have caused some disputes in the community and caused results to kind of go back and forth. So before we get started, I'll give a brief overview of how tonight's event is going to work. We will start out with drinks with my co-host Brianna Zawadsky, where Brianna will tell us all how to make a fun astronomy-themed cocktail with Steve. So Brianna, if you are ready, I'd like you to come in. Okay, and go ahead and take it away with the drink.
All right, awesome. So today I'm going to be making a black hole inspired drink for you all. What you'll need is cranberry juice, white rum, blue curacao, and grenadine. And also the key ingredient here, as this black hole inspired drink is mostly aesthetic, is some nice drink glitter. Hopefully you'll be able to see the sparkles when I'm finished making it because it does look really cool. Okay, so you're gonna need 2 ounces of cranberry juice. One ounce of white rum. 1 ounce of the blue curacao. And half an ounce of grenadine. So luckily this drink is already pretty dark before we add anything. So if you weren't able to find black drink glitter, it should still look pretty cool. I did get black specifically, and you don't need a lot. So I'll just go ahead and add in a tiny bit of glitter. Give that a stir. And watch it sparkle. I will add ice after this, but hopefully, if I shine my light on it, well, I knew it would be a little stretch to see it on camera, but I think that it's actually showing up decently. We have a really nice, like, dark purple, sparkly drink. So I hope you can see why it's black hole themed, and I hope you enjoy.
Okay, thank you, Brianna. I've got mine right here. So, Jack, could you turn your video on now and start sharing the screen?
Sure. Hello.
Great. So our first speaker is Jack Lubin. Jack is a graduate student at UC Irvine. And Jack, I'll let you take it away with your talk now.
All right, thanks. Hi, everyone. Thanks for that introduction, Arvind. And thanks for the opportunity to come speak to you today. I'm real excited about it. So yeah, my name is Jack Lubin. I'm a fourth-year graduate student at University of California, Irvine. My main focus is the discovery and characterization of exoplanets. And today I'm going to talk to you about a system that I've been working on for about the past year and a half. But it's actually not a discovery. It's quite the opposite. My work led to the death of a planet. But then as the title suggests, the lives and deaths, plural, I wasn't the first to so-called kill this planet. And in this talk, I'll take you a little through the history of this fascinating star and its planetary claims, and then I'll finish up with our current understanding of the system. So let's get underway. The star we're going to be talking about is Barnard star, and it was named after its discoverer, E.E. Barnard, shown here. He was born in 1857 to a very poor family in Nashville, Tennessee. His father actually died before he was born, and so times were very tough in his family. He received only 2 months of formal schooling, and they say the rest he learned from his mother. But money was tight, and so young EE did what anyone would do at age 9. He took a job. He worked as an assistant in a photography studio in Nashville, and this led to a lifelong fascination with photography. And that eventually led him to fascination with astronomy. And I found that the Venn diagram of people interested in astronomy and photography is pretty much a circle. And so the two really seem to go hand in hand. And maybe he was among the first to be fascinated by both, since photography was so young at the time. But fast forwarding a bit, after he got married, he finally saved up $360 to purchase his first telescope, a 5-inch refractor. And that's about as much as a backyard telescope will run you today, even. But back then, it was 2/3 of his yearly salary. And maybe he saw this as an investment because at the time, there was a wealthy benefactor who was offering prize money for each newly discovered comet. $200 per comet, not bad. Barnard found 5, and he used that $1,000 to build a house for himself and his wife. Later, he was quoted as saying that the house was built entirely from comets. From there, his reputation as an amateur astronomer grew, and he was offered a fellowship to Vanderbilt University just down the road. He ended up going, but not graduating. However, later in life, he was awarded the only honorary degree that Vanderbilt has ever given. And now this is the first of a few times that my life seems to have run semi-parallel to Barnard's. I went to Vanderbilt for my undergrad, but I did indeed graduate, and I have a picture to prove it. And in hindsight, this picture is almost too cool to be true because I promise you it is. The background building in this is actually Barnard Hall. It was a dorm that has since been torn down in the 5 years since I left. But yeah, it was named after E.E. Barnard. We all called it the Barnyard. And it was everybody's last choice for a dorm, mostly because it just wasn't very nice and it was very old. And maybe that's why they tore it down. But yeah. Anyway, after he stopped his studies at Vanderbilt, he worked for the school's observatory for a bit before moving out to California to work at the new state-of-the-art observatory owned by the also brand new University of California, and that was at Lick Observatory. At the time, it had the world's largest telescope, 36 inches in diameter, or about 1 meter. And for some reference, I routinely use the 10-meter telescopes at Keck Observatory in Hawaii for my own research. So quite an upgrade since then. At Lick, he applied his photography knowledge to produce images of the sky, and he was a very skilled observer. Here he is on the right with the 36-inch refractor. And to insert myself again into this talk, here I am also with the 36-inch refractor. This was a fun visit. But anyway, his biggest find while he was at Lick was the discovery of the 5th moon of Jupiter. And this was something I got to see while I was up at Lick that time. The lead astronomer, he took me into the archives and he showed me Barnard's personal observing notebook from the night that he made this discovery. And I think this is really, really cool. First on the right, there's a really great illustration that he made of Jupiter. You could clearly see the great red spot. You can see the cloud bands. He was clearly a talented illustrator as well as astronomer and photographer. And then on the left is where he records his discovery. He draws a very crude outline of Jupiter and he puts a dot off to the right. Let's zoom in on that. He labels that dot as an object and writes, "This must be a new satellite or elongation." This is really cool because this was the last time that a new planet or moon was discovered essentially by eye. The first 4 moons of Jupiter are the Galilean moons. They were discovered by Galileo in the 1600s as he looked through his telescope. And then a few moons of Saturn were found by eye through a telescope as well as the planet Uranus. But then there's this discovery by Barnard, 5th moon of Jupiter. And then all future discoveries of moons of Jupiter and Saturn and new planets like Neptune and even Pluto, if you consider that a planet, they were made by analyzing photographs. And now, of course, all exoplanets are discovered with computers. But this was just Barnard and a telescope, the last of an era of pure human observation. But after his time at Lick came to an end, he moved to Wisconsin and began to work at Yerkes Observatory, which was owned by University of Chicago at the time. This is where he made his most famous discovery in 1916, the star that was to be named after him, Barnard's star. He was looking through his old photographic plates, and he noticed that one star was not quite where it should be. And looking at more plates through history, he could see that see it move through the sky just as if it were this animation here. And it turns out this star has the highest proper motion of any star. So compared to background stars, it is just absolutely rocketing across the night sky. Although on the scale of a few decades, this animation starts in 1985 and moves to 2005. So 20 years is quite a bit of motion, but you would never really notice by eye. You need some telescopes. Later, the Barnard star was shown to be the second closest star system to our own, just under 6 light years away. So basically our next door neighbor. And because of that, it's been very heavily studied by astronomers in all subfields for the last 100 years. A little more about the star. It's a very red M dwarf star. So most of the light that it emits is in the infrared. And so despite being so close to Earth, it's actually too dim for you to see with your naked eye. You do need a telescope, but a backyard telescope is sufficient. It's very small in both mass and radius compared to our sun. And it's also a very old star, about 10 billion years old. Compare that to the age of our sun, and therefore the Earth, which is about 4.5 billion years old. So this is essentially twice the age. But also because it's so close to Earth and so often studied, Barnard star has become a favorite location among science fiction writers to place fictional planets to be used as like a galactic rest stop on the way back to Earth. This is just part of a whole Wikipedia page on Barnard star in sci-fi. And I was actually reading one of these, the Hyperion Cantos, while working on this star. And I was totally surprised by the inclusion of Barnard's world, which plays a fairly significant role in the story. So that was really fun, just seeing my own scientific interests merge with my artistic interests. It's just very special. But anyway, enough about the star. Let's talk about planets. And we're going to begin like we always like to do in a galaxy far, far away. Fair warning, there are a few kind of loosely related Star Wars references coming up. So I hope they make sense. And so just please stick with me on this. We have to start with episode 1, The Phantom Menace. Enter Professor Peter Van de Kamp at Swarthmore College in Pennsylvania. He had previously gotten his doctorate from University of California, and he had worked at Lick for a few years in the mid-1920s, but he didn't overlap with Barnard, who by that time had died. Somewhat fun fact, he advised and taught Nancy Grace Roman while she was a student at Swarthmore. Now the next generation of NASA's satellite searching for exoplanets will be named after her. Although it's important to note that she said Van de Kamp actually discouraged her from working with him. But anyway, Van de Kamp worked on a technique called astrometry, which is based on the idea that for any star-planet system or binary star system, both objects share their orbit their shared center of mass. This means that as the planet moves through the orbit, the star also moves around in a much smaller orbit. The sizes of the circles are proportional to the masses of the objects, and astrometry tries to measure this very small circular motion of the star. The orbital period of both the planet and the star are equal, so if you can measure the time it takes for the star to complete one circle, you also know the planet's orbital period. And also, if you can measure the size of the star's orbit, you can calculate the planet's mass. So the more massive a planet and the further away from the star that the planet orbits, the easier it is to measure this motion of the star. But either way, this technique requires very, very precise measurements of the star's position in the sky across long periods of time. And these are not easy measurements to make. So Van de Kamp used the telescope at Sproul Observatory at Swarthmore College to make photographic plates of the star field around Barnard star, looking for that small circular motion of the star, which would indicate a planet. He eventually published a paper in 1963 where he announced the discovery of a single planet orbiting Barnard star. A couple of years later, he published another paper adding a second planet to the system. These planets were both about half the mass of Jupiter, and they orbit at 12 and 20-year orbital periods. For some reference, our Jupiter orbits in a little under 12 years. So kind of a similar analog, at least one of them. Van de Kamp effectively published the first claims of planets outside the solar system. However, remember that this section is modeled after the Phantom Menace, and that's because both of these planet signals turned out to be phantoms themselves. And that leads into the next movie title, Attack of the Clones. While George Gatewood from Pittsburgh and Henrik Eichhorn of South Florida are not quite clones, they do kind of look like each other in these pictures. So I think it works. They tried to recreate the measurements of Van de Kamp, and they used 2 different telescopes to make these precise measurements of coordinates of Barnard's star. However, neither telescope detected the circular motion that Van de Kamp claimed. No circular motion of the star means no planets. And so this was a big blow to the credibility of these planets. Of course, a key tenet of science is the reproducibility of experiments. It seemed like these signals were not reproducible when using different telescopes than the original one that Van de Kamp used. This leads us into the final chapter of the prequels, Revenge of the Sith. In this case, the Sith is the telescope at Swarthmore College that Van de Kamp originally used. And its revenge comes in the form of this paper from John Hershey, another professor at Swarthmore. He reanalyzed the same photographic plates that Van de Kamp used originally to make the planet claims. And he found that in those photos, yes, Barnard's star is indeed moving in that circular motion like Van de Kamp claimed. However, he found that literally all of the stars in the photos were moving in the exact same circular motion. And it is so improbable that hundreds of stars have planets at the exact same orbital periods and masses that it is essentially impossible. And this result pointed to the culprit. There was an issue with the telescope. Hershey was able to cross-match the circular motion of the stars to times when the telescope had been either upgraded or cleaned. The circular motion was merely an artifact of the telescope's instrument, not anything astrophysical. And this was the nail in the coffin for Van de Kamp's planets, and thus the first death of Barnard's planets. Now, all this said, Van de Kamp himself never conceded that his planets were not real. He even published 2 more papers afterwards, refining the mass and period measurements of both planets. And then he died in 1995, still believing he had discovered the first exoplanets. And sadly, he died actually just a few months before Michel Mayor and Didier Queloz published the discovery of the first confirmed exoplanet, 51 Pegasi b, for which they shared the 2019 Nobel Prize. With that discovery, the exoplanet era began in the mid-90s. We started finding dozens, then hundreds, and then thousands of planets, but still no one could find a planet around Barnard's star. But then we enter the original trilogy, A New Hope. In 2018, a team of international astronomers announced the discovery of a super-Earth planet orbiting Barnard's star. They measured it to be 3.2 Earth masses on a 233-day orbit. Their paper was published in Nature, a very prestigious journal with a lot of excitement throughout the community and among the sci-fi community. This team used a different technique to search for the planets, called the radial velocity technique, or the RV method. The RV method looks for the motion of the star, just like astrometry, but in the radial direction, in and out of the plane of the sky. We do this by taking spectra of the star and measuring the location of the absorption lines. Like in this animation, as the planet moves around the star, it gravitationally tugs on the star. That motion of the star produces a Doppler effect, which shifts the absorption lines left and right. If we can measure those absorption lines moving back and forth periodically, then we've measured the planet signal. This is a really powerful technique that's been used to discover hundreds of planets and then to measure the masses of thousands more. But it does have its limitations, and not all was as it seemed. Episode 5, The Empire Strikes Back. In this case, myself, along with my collaborators at UCI and Penn State, we represent the Empire. The thing about the RV method is that it really depends on the precise measurement of the location of those absorption lines in the stellar spectrum. Planets can cause these lines to move. That's what we're looking for. But there are other phenomena that can also make the lines move. These phenomena fall under a broad category, which we call stellar activity. And it's essentially like weather patterns on the surface of the star. So things like star spots, like on the left, or bright spots, like things on the right, they can cause absorption lines to shift, or at least appear to shift, without any planet needed at all. So we can get tricked into believing a planet is in the system, when really it's just the result of the stellar activity masquerading as a planet. And here's an animation of what I mean. As a star spot rotates into view, the absorption line becomes distorted, and this distortion can make us think that the line itself has moved, like we would expect a planet to do. But because the star spot comes around once per stellar rotation, that can make us think that the line is shifting just like a planet at a period equal to the rotation period of the star. Stellar activity is currently one of the biggest hindrances to planet detection using the RV method. Planetary signals must persist through time because, well, the planet is always orbiting the star. But stellar activity signals are temporary. They live for a few rotations of the star before dying off and then re-emerging. This behavior introduces another problem, aliasing. I think this is the best figure to describe aliasing. The idea is that if you have a signal, but you can only sample it a few times, if you're not careful about your sampling, you won't have enough information to properly reconstruct the signal. So here we have a set of observations, the black dots, and we can fit two different signals equally well to this data set. The two signals are then aliases of one another because given the data in hand, we cannot tell which period is the true period. This is kind of similar to like that dress that everyone was arguing about a couple of years ago. Why there's as black and blue. Personally, I see gold and white. We're all working with the same data, but we can't definitively tell the difference due to the sample that we have. Because stellar activity signals are not strictly periodic, they're more susceptible to aliasing. And so these two things, stellar activity and aliasing, were the subject of a paper that I recently led, which was accepted for publication in the Astronomical Journal. And here I want to highlight some collaborators I have from Penn State. Those with red underlines are currently at Penn State, and those with green have been at Penn State within the last few years or so before moving on to other institutions. But so we revisited the data set from the team that claimed a planet around Barnard star, as well as we collected new data from a more precise instrument on a bigger telescope. And we concluded that the signal associated with the planet is instead an alias of stellar activity. What ultimately led us to this was this conclusion was that there was a subset of data right in the middle of the observing baseline where the signal associated with this 233-day planet was really strong, but then in other subsets, the signal was essentially non-existent. This is worrisome because, again, planet signals should persist while stellar activity signals come and go. Also, the rotation period of Barnard star is 142 or so days, which is a one-year alias of 233 days. You can see that in the equation at the bottom. So essentially, we concluded that the signal associated with the planet was instead due to stellar activity, and therefore the planet is a false positive detection. So effectively, we have killed this planet. And I will say that it brought us, and me in particular, no joy in killing this planet. I, for one, came to grad school to discover planets, not to kill them. And so this work and this paper are a little bittersweet to me. I mean, I'm very proud of it, don't get me wrong, and I stand behind it 100%. And the lessons that we learned analyzing this data are going to be very valuable to both us and the larger community in the future when we're looking for planets. But at the end of the day, we removed a planet, and that's not something that we want to do or like to do. And on that bittersweet note comes the final chapter of the original trilogy, The Return of the Jedi. In this case, the Jedi which are returning is a planet around Barnard star. It's important to note that our paper did not rule out planets forever in the system. It only showed that this one particular planet claim was a false positive. There are many reasons to believe there could be a planet one day around Barnard star. We know that planets around M dwarfs are very common. That's a point in its favor. We also know that there are different limitations to our planet hunting techniques. Our instruments today just might not be sensitive enough to detect small planets. And this is kind of represented by that frontier region at the bottom right corner of this plot. Currently, we just can't detect these planets, but we know that they're out there, and possibly one or more is orbiting Barnard star. So while I don't know if Barnard star has planets, what I do know is that the story of the star is not over. It is still a very popular target of amateur and professional astronomers alike. And definitely the exoplanet subfield is not through with this star. Our team is continuing to observe it, and there are multiple other teams that have Barnard star on their survey lists using the newest generation of extreme precision instruments. This star continues to fascinate, and it will for a very long time. Hopeful that one day there will be a confirmed exoplanet in the Barnard star system. So with that, thank you. I'd be happy to take any questions.
Thank you, Jack. So for the viewers at home, if you do have questions, just put them in the YouTube chat and I will check those out and relay them to Jack here. But I guess I can kick it off. So Jack, that was a great talk. I really liked the history of Barnard himself, as well as the star and the potential exoplanets. So we're actually really curious, why was this rich benefactor paying people to find comets in the first place? Like, it's great that that happened because it gave birth to his whole astronomical career, but why would somebody do that?
Yeah, comets were like one of the most interesting things in the night sky in the, earlier than say year 1900. People were just really fascinated by comets, and I think in part for like, quasi-religious or spiritual reasons, people found comets to be omens, good or bad, depending on what culture you might be subscribing to. But so yeah, people were really fascinated by comets, and they're also just honestly quite beautiful. I don't know if anyone had a chance last year, kind of in the heart of COVID, when everything was locked down. There was a comet that could be seen by naked eye over North America. And I had a chance to go observe it. It was just a really cool experience. So people just love comets, I think. And so at the time, there was this, again, this big fascination with them. And so this wealthy person wanted to find more, and he wanted to incentivize people to find more. And so he put his money where his mouth was. And luckily, Barnard rose to the challenge.
Okay, well, I'm glad that worked out. Yeah. So another question then. So it seems like astronomers have been paying a lot of attention to Barnard star in particular with respect to the presence of exoplanets. Are there any other stars like this that have been receiving this much attention or controversy?
Well, a couple that are controversial do come to mind. So my advisor, Paul Robertson, he had a controversial paper in 2014, I believe it was, about Gliese 581, where he ended up doing a big reanalysis of the RV data and determining that a couple of the planets in the system were, again, associated with the rotation period, and something had been aliased, and is kind of a similar situation in some accounts. And so he ended up removing planets from that system, which was a bit controversial at the time, although now it's fairly well accepted. There are other stars that get as much attention in terms of just pure number of observations. Stars like Tau Ceti, which is a very, very bright G-dwarf star. It's very similar to our sun. And so because it's so bright, it gets a lot of observations as well. And in that system, we found planets as well. And so that's what's kind of so frustrating about Barnard stars. It's been looked at for so long by so many people, specifically looking for planets. And so far, we've come up empty-handed. Whereas other stars, it seems that planets just kind of fall out onto us, and we have too many we don't know what to do with.
Okay. Is there a reason then that we care so much about Barnard star aside from it being nearby?
Yeah, and the main reason we care so much about Barnard star has nothing to do with planets necessarily. It's that Barnard star is considered among astronomers to be like, the standard star for the M dwarf class. So a lot of M dwarfs are compared to Barnard star. And also Barnard star is thought of as the radial velocity standard. So when we build new instruments capable of making these radial velocity measurements, we often start by looking at a set of standard stars to kind of help calibrate the instrument. And we observe them to make sure that we're getting data that we expect, just because these stars have been so well studied that we have a good idea of what to expect in the data. And so Barnard star being the standard star for calibrating future instruments, we need to make sure that we understand it very, very well. We need to make sure we understand if there are planets, and we need to make sure we understand its activity cycles very well if we're going to continue to use it as a standard.
Okay. So I guess given that, as you said, people observe this a lot, are there regions of parameter space that can be ruled out for future planets? You talked about there definitely being the possibility of exoplanets orbiting this star, but could we rule out, say, a Jupiter or something orbiting it?
Yeah, we can do a lot of ruling out of fairly high mass planets across a large range of orbital periods. like for example, measuring a one Jupiter mass planet at the distance of Jupiter, which is 5.2 AU, I think, from our own star. But in our own star system, Jupiter imparts something like 12 meters per second, I think it is. No, it's 28. Sorry, it's 28 meters per second. There's a 2 in there somewhere. And so that we could, no problem, we could measure that. Barnard star is even smaller than the sun, so it should, a Jupiter mass object at a 5 and change orbital semi-major axis should impart an even larger RV amplitude. And so it should be like shooting fish in a barrel to find these, massive planets around Barnard star. Of course, there is a point where the planet separation is far enough from the star that the signal becomes so weak that maybe we couldn't measure, a very large planet. But for the most part, among somewhat reasonable orbital distances, we can very easily detect planets, of say 20 plus Earth masses. Again, out to certain distances. But the real kind of trick is where you get these small planets, like this one that was claimed by the first team, where it was only 3.2 Earth masses at an orbital period of 233 days. The RV signal associated with that planet was just over a meter per second, which is right at the threshold of our capabilities right now. And luckily, we have a new generation of extreme precision instruments that are breaking through that 1 meter per second threshold. Instruments like HPF, the Habitable Zone Planet Finder that we use to do our observations of Barnard star. And then also there's another new spectrograph, Arvind, I know you've worked a lot on it, NUID, which is also capable of measuring even smaller signals. But the problem is that as you get these small planets at big separations from their host star, the amplitudes of these signals become so small that we just haven't been able to detect them with our current instrumentation, although that is very rapidly changing. And so it's very exciting. It's a very exciting time to be in exoplanet science right now.
All right. So I'll finish up with one last question, Jack. So I know that any answer here is going to be pure speculation, but what do you think about the potential for habitable exoplanets around Barnard star?
Yeah, I mean, it's a great question. And I mean, a lot of people are optimistic. The thing is that for the sun, the habitable zone is, roughly 1 astronomical unit, a period of 365 days, just because that's where the Earth is. And we know that it's habitable. These M dwarfs like Barnard star, which are so much smaller, and so they're a lot cooler in temperature, the habitable zone is much closer to that star. And while I don't actually have a number off the top of my head, I would guess that the habitable zone, for Barnard star is in the order of, 30 to 50, 60, 70 days, somewhere in there. And so at those orbital periods, planets of, terrestrial nature that are more rocky than, say, gaseous, we're kind of like, maybe we can detect them, maybe we can't. We could probably have detected, if this planet, this 3.2 Earth mass planet, had been at 50 days, we might have been, in terms of just raw signal amplitude, we might be able to detect that. But if it's Mars mass, which is about 1/10 of the mass of Earth, we still could not do that. And so maybe there is a little Mars-like rock orbiting Barnard star at 50 days. And maybe it's at the right distance, that it's lush with water, and who knows. But we just don't have the sensitivity at this time. But again, that is rapidly changing, and so that's why people are continuing to observe this star.
All right. Thanks for the talk. I know we all appreciated the Star Wars references.
Thanks.
I'm personally hoping to follow any new discoveries around Barnard star very closely. Yeah, thanks for joining us, Jack. And with that, you can head out. And Steve, are you ready to start on trivia?
I am. Can you see me?
I can, yes.
Great. Let me share my screen. All right, you should be able to see the trivia screen right now. If you want to play tonight's If you want to play tonight's trivia, I pasted a link into the YouTube chat. Just copy and paste this tiny URL into your address bar, and you'll get taken to a Google form where you can put in responses. The way we'll do this, there are 15 questions in tonight's trivia, so take your best guess at each question. We'll go over each question twice to start off with, and we'll do the answers at the end of the night. Be sure to give your team name an astronomy-themed name, because the best name will win ties. The winner of tonight's trivia will get some amazing Astronomy on Tap themed prize of their choosing, whether that's a mask, a coaster, a bottle opener, or perhaps a beer koozie, if that tickles your fancy. So without further ado, let's jump into the trivia. Each question will look a little bit like this. It's just an example question. What color is Neptune? I'll read out the 4 answers for you, and then obviously at the end, we'll go through the correct answers. Obviously, Neptune is blue in color. So without further ado, let's jump into some trivia about astronomical controversies through the ages. And we'll start off with this astronomer, according to legend, said "Et puis se mouve," excuse my terrible foreign language, and yet it moves, upon being forced to recant his heliocentric views by the church. Was that Johannes Kepler, John Flamsteed, Galileo Galilei, or Nicholas Copernicus? So which astronomer said that upon being forced to recant his views by the church? The second question is, of the International Astronomical Union standards for a planet, Pluto failed to meet this criteria and was therefore relegated to dwarf planet status in 2006. Is that being roughly spherical in shape, orbiting the sun, having an atmosphere, or clearing the neighborhood of its orbit? Again, which criteria to be a planet did Pluto fail to meet, relegating it to dwarf planet status? The third question is, in 1979, Fred Hoyle, an astronomer, claimed that chemical similarities with interstellar dust suggested that this came from outer space. Did he suggest salt, the common cold, deep sea mineral deposits, or laundry lint? Again, what did astronomer Fred Hoyle claim come from interstellar space because of chemical similarities? Question 4. To explain strange perturbations in Mercury's orbit, Urbain Le Verrier predicted a planet orbiting very close to the sun. What did he call this non-existent planet? We now know it doesn't exist. Did he call it Dantooine, Vulcan, Vogosphere, or Thessia? Again, what did Urbain Le Verrier call a predicted planet orbiting very close to the sun that we know doesn't exist? Question 5. Dark matter is invoked to explain galaxy rotation curves, galaxy cluster gas temperatures, and so on. What is the name and acronym of the controversial theory that explains these phenomena by simply altering the laws of physics? Is it alterations to systematic theories of physics, ASTP, relativistic accelerated phenomena, or REAP, modified Newtonian dynamics, or MOND, or attenuated rotation via physical adaptation, ARPA? What is the name of the controversial theory explaining away the need for dark matter? Question 6. In 1949, Fred Hoyle, the same Fred Hoyle as before, argued that the universe was in an eternal steady state of expansion and creation of matter from nothing. He ridiculed the idea that the universe began in a tiny point of incredible mass, and he called it, was it the horrendous space kablooey, the primordial atom, a big bang, or the singularity at the start? Again, what did astronomer Fred Hoyle jokingly call the theory that the universe started in an incredibly dense state? Question 7, kind of in a similar theme to the talk we just heard. Though in 2015, the discovery was shown to be a statistical error, a team of astronomers announced in 2012 they discovered an Earth-like exoplanet orbiting which nearby star? Was it Polaris, Alpha Centauri b, Proxima Centauri, or Ross 128? Again, what star did a team of astronomers announce a Earth-like planet around, only for that discovery to be shown a statistical error in 2015? Question 8. How exactly did famous Danish astronomer Tycho Brahe lose his nose? He wore a metal prosthetic for the rest of his life. Was it A, his pet moose bit it off, B, a sword duel with his cousin over who was a better mathematician, C, a hunting accident where a crossbow misfired, or D, a telescope fell on his head? Again, how exactly did Danish astronomer Tycho Brahe lose his nose? Now we have a bonus question, not really astronomy related, for a half point, so it might break a tie. Speaking of Tycho Brahe, how did his pet moose die? Not exactly astronomy related, but too good to pass up. Was it A, dying of old age in 1610, several years after Tycho Brahe? B, did Tycho lose a bet with his apprentice, who cooked the moose in a pie? C, a hunting accident where a crossbow misfired? Or D, the moose drank too much beer and fell down a flight of stairs? For a bonus question, 1/2 point, how did Tycho Brahe's moose die? Back to astronomy-themed questions. William Herschel discovered the 7th planet in 1781. Before its current name was chosen, which one of these was not a name used for Uranus? Was it Neptune, Great Britain, King George's star, Herschel, 34 Tauri, or Minerva? Again, before it was given its current name, which one of these was not a name used for the planet Uranus? Question 10. Newton and Leibniz are both credited with discovering calculus, but today we use Leibniz's notation. What did Newton call his approach, first written in 1666? Did he call it the way of integrals and derivatives, the method of fluxions and fluents, the approach to maximum area, or the superior and inferior gradients? Again, what did Newton call his approach to calculus, which we don't use much today anymore? Question 11. Robert Hooke and Isaac Newton had a long-running feud over who first described the inverse square law of gravitation. Today, we know Robert Hooke with Hooke's law. The description for what? Is it the volume of a pyramid, the force by a spring, the formation of memory, or the motion of a comet? What does Hooke's law describe? Question 12, Hubble's law, describing the recessional velocity of distant galaxies, is now also named after this Belgian astronomer who independently discovered the relation a few years earlier. Was that Charles-Jean Nicolas, Walter Baade, Fritz Zwicky, or Georges Lemaitre? What Belgian astronomer independently discovered the recessional velocity of distant galaxies a few years before Hubble? Question 13. From 2004 to 2005, considerable controversy surrounded the discovery of this dwarf planet. One team, led by Mike Brown of Caltech, accused another of fraud, accusing that other team of accessing their telescope data without credit. Was the dwarf planet Atasina, Eris, Haumea, or Makey Makey? Which dwarf planet was the subject of this controversy? Question 14. Before the work of Cecilia Payne and Margaret Burbidge and others showed that the sun produced power via fusion of hydrogen, what did Lord Kelvin suggest as the explanation for the sun's luminosity? Did he suggest matter-antimatter annihilation, that the sun was a hot piece of metal glowing brightly, repeated impacts by meteors heating the surface, or radioactive decay? What did Lord Kelvin hypothesize as the explanation for the sun's luminosity? And our final question for tonight is: the Italian monk Giordano Bruno was burned at the stake by the church in 1600 on charges of heresy. Which one of these was not one of his heretical opinions? Was it other stars are suns with planets? Other planets might have life? The universe has no center and is infinite? The Earth orbits the sun? Or a seventh planet orbits beyond Saturn? One of these was not one of his heretical opinions. Which one is it? So there's our 15 questions and one bonus question. Now I'm going to go all the way back to the start and run through the questions again very quickly so you have a chance to catch any you miss. First question, which astronomer, according to the legend, said, "And yet it moves," upon being forced to recant his views? Of the IAU standards for a planet, which one did Pluto miss out on and therefore was relegated to dwarf planet status? In 1979, what did Fred Hoyle claim came from interstellar space because of chemical similarities? What did Urbain Le Verrier call the planet he predicted orbiting close to the sun to explain perturbations in Mercury's orbit? What is the name of the theory that explains away the need for additional dark matter in galaxies and instead just modifies the laws of physics? In 1949, what did Fred Hoyle jokingly call the idea that the universe exploded out of an incredibly dense point? What nearby star had a planet announced in 2012 only to have that view countered and shown to be a statistical error in 2015? Excuse me, what's the host star name? Number 8, how did famous Danish astronomer Tycho Brahe lose his nose? The bonus question for a half point, because it's not super astronomy related, how did Tycho Brahe's pet moose die? Number 9, which one of these was not a name for Uranus after it was instead of its current modern name? Number 10, what did Isaac Newton call his approach to calculus that he published in 1666? 11, Robert Hooke and Isaac Newton had this long-running disagreement, but today we know Hooke's law, and what does it describe? 12, what used to be called Hubble's law is now also named after this Belgian astronomer who independently investigated it a few years earlier. 13, which dwarf planet was the subject of considerable controversy over its discovery, with accusations of fraud being thrown about? Number 14, what did Lord Kelvin suggest as an explanation for the sun's luminosity before we knew that it was produced via fusion in its core? And finally, which one of these opinions was not a heretical view of monk Giordano Bruno when he was burned at the stake in 1600s? Which one is not one of his heretical opinions? So that's our trivia for tonight. Make sure you get your answers in before the end of Astronomy in the News, which Brianna will take over in a few moments. And at the end of the show, we'll go over the answers, and also I'll reveal the winner.
All right, let me get my screen shared. Awesome. So today for Astronomy in the News, I'm going to be talking about several Venus missions that were announced at the beginning of the month. If you've been tuning in the last few months, we have been talking quite a bit about Mars, and now we'll just shift on over to Venus for some upcoming things. So there are 3 new missions in the works, 2 from NASA. There's NASA's Da Vinci Plus and Veritas, and then there's the European Space Agency's Envision. And so I'm just going to go through and talk a little bit about each probe, when we're going to expect those probes to launch, and what their main science goals are. starting off with Da Vinci Plus. It stands for Deep Sphere Venus Investigation of Venus's Chemistry and Imaging. And one thing that you can very quickly learn about astronomy is that there are some pretty interesting acronyms, and I could probably have a whole talk about that. But anyway, Da Vinci Plus is going to be an orbiter and a probe. It's going to launch around 2029 or 2030, so we're going to have to wait a while, which will be the case for all of these exciting new missions. And it's expected to arrive at Venus's atmosphere around 2031 or 2032. The main science goals of Da Vinci Plus are to understand the origin and evolution of Venus's atmosphere, investigate atmospheric composition and interactions with the surface, and take high-resolution pictures of Venus. And on the right, we just have an artist's depiction of what the probe will look like. Since they're not going to be launching for like 8 or 9 years, all we have at the moment are concept art, really. So hopefully over the next 5 to 10 years, we'll be able to get some really exciting updates on the building progress, and then eventually the launch, and eventually the results. The other NASA mission that got selected is Veritas, which stands for Venus Evasivity, Radio Science, INSAR, Topography, and Spectroscopy. This one is just an orbiter, whereas Da Vinci Plus was an orbiter and a probe. Veritas is expected to launch a little bit earlier in 2028, so that will be relatively soon. I'm sure it'll come faster than we all want it to. And its proposed mission duration is 3 years. And there we have on the right the concept art for Veritas. Its main science goals are to understand how geologic features have changed over time on Venus, learn about the current geologic processes on Venus, and determine whether water was or is currently present on the surface of Venus. The last mission, this one is from the European Space Agency, is Envision. It's an orbiter. It's going to be launching in 2031 and will hopefully arrive at Venus in 2034. It has the planned mission duration of 4.5 years. And its main science goals are to perform high-resolution radar mapping, understand the relationship between geologic activity and atmospheric activity, and investigate why Venus and Earth evolved so differently. Some of you may know that Venus and Earth are similar in many respects, but have had some pretty different formation histories, and as a result have very different features. So Envision is going to look into that a little bit and help us understand what exactly happened to make such a drastic difference in Earth and Venus. Entered on the right is not actually any instrumentation for Envision, but just some instrumentation that they are using to build Envision's instrumentation. So it's from a different mission, but it'll be largely the same idea for this one. So obviously all of these missions are going to be in the 2030s by the time we're getting results. So we will have to be very patient, but we're going to be learning a lot about Venus, and with 3 great missions coming up, hopefully by the 2040s, we'll have a very good idea of what's going on on Venus and in Venus's atmosphere. Okay, so I'll pass it back to Arvind.
Thank you, Brianna. And as Steve said, make sure that you have your trivia answers in now if you plan on submitting. With that, I'm going to ask Taylor to hop in. Taylor, could you turn your screen on and start sharing? Awesome, welcome. So Taylor is a graduate student at the University of Chicago. He studies the expansion of the universe and the Hubble constant. With that, Taylor, you can take it away.
Can you hear me? Is it?
Yeah, we can hear you.
Okay, perfect. Sorry, I'm using a new mic. Okay, so as Arvind introduced, I'm a graduate student at the University of Chicago, and I work on measuring the expansion rate of the universe, which I'll get into in a second. So I want to talk about a really exciting kind of debate that has emerged in my field in the last few years, which is called the Hubble Tension, which I'll get into again in a second. And it's kind of summarized as this big cosmic conundrum where we are kind of debating how fast the universe is really expanding. And this disagreement could, if real, could upend our kind of standard model of cosmology that's kind of basically predicted every observation we've seen for the past 2 decades to frighteningly good accuracy. And I'll explain why that's terrifying and why people want to break it also in this talk. So really briefly, who am I specifically? I'm an observational cosmologist. The observations I take, or rather that I sometimes ask Hubble to take for me, are designed to advance our understanding of the cosmos. Can't see my cursor. I guess constrain its current dynamical state, which we can use to understand its past and perhaps most excitingly, its future evolution. Some fundamental questions that kind of underlie all of my work, the big questions that keep me up at night, like we call them. How did it all begin? How did the universe begin? What is the nature of the dark energy in the universe? How will the universe evolve? How will it end? And to do this, I use a special class of stars called standard candles. And these standard candles are astronomers' best tool for measuring distances to other galaxies. And I'll get into a few examples also later in the talk. So I use the Hubble Space Telescope to measure these distances to other galaxies. And basically to measure the expansion rate of the universe, we pair those measurements of distance with measurements of what we call the recession velocity, which one of the trivia questions alluded to in discussion of the Hubble-Lemaitre law. Basically by pairing the distance with the apparent receding velocity, so how fast the galaxy is moving away from us, we can constrain the expansion of the universe. And so again, what I will discuss today is basically what measurements define this debate over the expansion rate of the universe, this cosmic conundrum, and how can it be resolved? And a hint is new, bigger telescopes. So to summarize our model of the universe, you'll see here a figure that I think a lot of my colleagues see all the time and get tired of seeing, but this is kind of the best depiction of how we think the universe evolves over time since its inception. So basically in the earliest years of the universe, this very hot, dense quantum gas at millions and millions of degrees, so hot that light can't even propagate throughout the universe. It's just a hot, basically it's like the interior of a star, but even hotter and even more chaotic. And kind of the most salient part of this is that this quantum gas, so quantum mechanics basically dictates that even just particles existing as they are have fluctuations in their energies, just on account of it's just inherent to these small subatomic length scales. There are fluctuations. So particles become waves on the quantum scales, and that's why you get kind of a range of energies. And anyways, so these quantum fluctuations kind of imprint 1 part in a million fluctuations in the temperature of this primordial soup that we call it, which is the origin of the Big Bang as well. And these tiny 1 part in a million fluctuations in the temperature, which is due to 1 part in a million fluctuations in the density of this primordial plasma, actually plants a seed for the growth of structure. Oh, I can see my mouse now. For the growth of structure. So you can see here the quantum fluctuations, a map of those. So redder regions are less dense and bluer regions are more dense. And you can see that they plant the seeds for the evolution and the growth of structure in the entire universe today. And so this depiction here, the grid, is a 2D visualization of the universe. And basically these quantum fluctuations get blown up hugely by an early, which I'm not going to talk about here, but it's sort of related in a convoluted way, which I'll briefly cover, called inflation, where the universe increased in size by, we call it E-folding, which is the number of exponentials, which is about 3 to the 50th power. I don't really know exactly how many zeros that is, but it's something like 30, 20. Anyways, the universe exploded. These quantum seeds then led to the development of structure and galaxies in our universe, which evolved to the present day. And what this means is that we can make measurements of how the universe evolves in time using things like standard candles. And by measuring the expansion rate as a function of time throughout the history of the universe, we can actually constrain the components of the universe into kind of different parts classified into different substances based on their effects on the evolution of the universe. And so what's really interesting and what I really like to show here for perspective is if you look at this 4% number, sometimes I can see my mouse, sometimes I can't. I'm so sorry, I'm pointing to a random spot. So if you see the free hydrogen and helium part of this pie chart where it says less than 4%, that's kind of the dominant amount of what we call normal matter in our universe. And so basically what this tells us is that 96% of the universe is made of substances that we can't observe, but we can measure the effects that these invisible substances have on the expansion rate. And that's how the terms dark matter and dark energy come into play. So dark matter has applications outside of cosmology. As mentioned earlier, the rotation curves of galaxies, mergers of galaxies, the distribution of kind of satellite galaxies that we call them around large galaxies like the Milky Way. But dark energy has no definition outside of how we observe it affecting the expansion rate of the universe. And that's a really interesting point because we can actually flip it and use measurements of the expansion rate to constrain the properties of the dark energy. And so to quickly introduce what I even mean when I say the expansion of the universe, what that means is that the space is not expanding into anything. Truly, space itself is stretching. So if you picked a point from us and you observe the expansion of the universe, every galaxy around us in every direction appears to be expanding away from us. But if you interpret that just as that one point, it would seem there's a center, but there isn't a center, because if you go to one of those other galaxies that's moving away and you put yourself there, every galaxy around you is receding from you. It's true everywhere in the universe. And that's the cosmological principle, that Hubble expansion is occurring everywhere uniformly. And this can stretch things like the wavelength of light. And that's how we measure the speed at which these distant galaxies are moving away from us, and to measure the expansion rate. So a brief history, I think I want to speed up a little, but this is the history of measuring the Hubble constant in time. So starting with Henrietta Swan-Leavitt, who quite revolutionarily discovered that brighter Cepheids, so this class of stars called Cepheid variables, they pulsate what we call radial pulsations. And what that truly means is the envelope, the puffy gas surrounding the core of the star, actually expands and contracts. And we can observe that expansion and contraction as fluctuations in the brightness of a Cepheid as a function of time. And what Henrietta Swan-Leavitt discovered is that the Cepheids that are kind of puffier also pulsate, so they contract and expand at a slower rate than the less puffy, less bright spots. So what we call longer period Cepheids also are intrinsically brighter, and they follow a regular relation called the Leavitt law, which Edwin Hubble in 1929 used to first measure the expansion rate of the universe. I can't hide my camera on the right. So Hubble used this Leavitt law, the Cepheids, to measure the expansion rate of the universe, and he measured a value of 500. And for reference, the canonical value today is around 70. And so Bada corrected this measurement. I don't want to get into that too much, but what I really want to get into, because it's very relevant to today, is around the 1960s, the 70s, all the way up to the 90s, there was a debate over, similar to today, over the expansion rate of the universe. This is called the factor of two debate. And so Sandage on the bottom left, who was Edwin Hubble's kind of protege, his top student, advocated for a value of 50. And Gerard de Vaucouleurs over here advocated for a value of 100. And these two regularly debated in the literature over this value. And it would turn out, with the launch of the Hubble Space Telescope, neither was correct, and the value was actually somewhere in between. Oh, I got stuck. Somewhere in between, and they had been underestimating their error bars. And so, for reference, you see in the top left and the bottom left, I plot their values, the 150, relative to measurements of the Hubble constant in this century using the Hubble Space Telescope. So the one from the point in 2001, I'm sorry, I wish I could see my cursor and point you here, but the leftmost blue square here was the first measurement of the Hubble constant using the Hubble Space Telescope as one of its key projects to reach mission success. And over time, the error bars have shrunk as we split into different methods, but the values have diverged depending on which method you use to measure the expansion rate. So for now, to define the Hubble tension, I just want to talk about the Cepheids at the top here, which I introduced using the Leavitt law, and another one called the cosmic microwave background. And this is actually observing those quantum fluctuations I talked about earlier. You can actually determine the size, the typical size of those quantum fluctuations, and to extremely high precision, 0.1%. And using that, you can extrapolate kind of the size of those fluctuations to the present day to predict, using your cosmological model, what the expansion rate of the universe today should be according to our model. While the Cepheids, you make a direct measurement in the nearby universe using stars that we can empirically measure the brightnesses and distances to. And so what the Hubble tension is, it's this divergence between methods, but not just different methods measuring the same thing. They're slightly different because one method is measuring the Hubble constant, or the present day expansion rate, directly. The other one is inferring it from the present day expansion rate from the earliest light of the Big Bang, and extrapolating it using our best model of the universe to today, like the plot I showed that showed the quantum gas preceding the galaxies to the present day. And so basically, if those two diverge, that's a hint that our understanding of the universe may be flawed and it needs some additions. So this is just summarizing what I just said. So how does my work fit into all of this? So as I said, I use the Hubble Space Telescope to measure what are called red giant stars in the outskirts of galaxies 50 million light years away. These are really the most run-of-the-mill stars you can find, but they're rare because they evolve very rapidly. So stars, just like our sun, will eventually, when they exhaust their core hydrogen, the hydrogen content in their core where they're fusing, there's a fusion reactor going on. Once they run out of hydrogen, it becomes a helium core. A phase of kind of unstable burning will begin, and the star reacts by puffing up to about 100 times its size. And in the case of our solar system, that will mean the sun will engulf the Earth. And it turns out that these kind of crazy luminous, so luminous means very bright, stars, they actually exhibit a remarkable regularity in their brightness, their intrinsic brightness, and it's one of the most accurate tools we have for measuring distances. And I use them to measure the expansion rate of the universe. I don't know if this will work. I doubt it. don't freeze on me. I hope you can see this, the yellow, this is a depiction of the sun, an artist's representation of how the sun, so there you can see it engulfing Mercury. And this is what the sun will do when it reaches a red giant phase. And so when stars get bigger, they're also brighter to us because they have more area emitting light. And so I actually measure these red giant stars to measure the distances to distant galaxies. And of course, it ended it. Let's try again. Closed my whole thing. All right. So this is how we measure these red giant stars, and basically we point to the outskirts of galaxies, and you can see them here as these orange dots. And what we measure is actually a value in between the Cepheid and the kind of quantum fluctuation method that you can see here in red. And what this means is it kind of calls into question, is the Hubble tension real? So to kind of summarize, so the blue points here are the Cepheid measurements, and the black points are using the quantum fluctuations from the Big Bang, extrapolating to the present day, right? So the blue and the black, the difference between them is the Hubble tension. However, using this red giant method, we found a value that kind of agrees with both, and actually better agrees with the model prediction. So that could be evidence that there isn't really a tension, and there may be measurement errors and human errors causing the Cepheid value to be biased. And so this has spurred a huge kind of debate in the literature that is still going on. So you can see lots of claims of high precision, high accuracy measurements, which may be optimistic. You can see some very catchy titles, The Hubble Tension Bites the Dust, and everything throughout the past few years has been debated and questioned. And so just to get to my take, because I think I'm probably just out of time, I think the Hubble tension is real, but the absolute difference right now we're seeing between the Cepheids and the quantum gas kind of extrapolation, right? The model predicted expansion rate, I think it's being inflated by underestimated error bars in the Cepheid measurements. So one reason I think that is because with the current Cepheid measurement and the model prediction, that difference is extremely hard to explain with kind of the most commonly developed theories and models to kind of bridge that gap between those two measurements. However, the what we call the model parameter space increases by orders of magnitude with a value of 70 or 71 that we're seeing with these red giant stars, like the end phase of the sun when it will engulf the Earth. And to me, that may be an alternate indication of, okay, well, if we can't actually explain what's happening with the Cepheids and the model prediction through a new model, maybe it's telling us that the Occam's razor, we call it, may be telling us that just the Cepheid measurements could be wrong. And this is a question of precision versus accuracy. And so this is the summary of my take. I think the accuracy is being overestimated because of an overestimation of the precision in current measurements. And it's really not possible to answer whether this is true or not until we get a technological advancement to really resolve the problems that could be plaguing the Cepheid measurements, which we have many ideas for what they could be, and we just need to test them. And just to conclude, to do that, we'll need the James Webb Space Telescope. So our team was lucky enough to be awarded time on the soon-to-launch Webb Telescope to assess this exact problem. It will observe the red giants and the Cepheids at the same time in the same galaxies. And the remarkable thing about Webb is it's 10 times more sensitive than Hubble in infrared wavelengths, which is kind of where it's most accurate to measure both of these classes of stars. And so we'll use the Webb measurements to see if there is an issue with the Hubble telescope measurements of the Cepheids, and also to improve the red giant measurements. And among other things, the Webb will measure, observe the first galaxies ever born in the universe may detect signs of life on other planets, and of course help us understand the expansion of the universe. So Webb will usher in a fundamentally new understanding of the universe. And so I guess now to actually conclude, to quote my PhD advisor and transitively Carl Sagan and transitively Thomas Jefferson and Laplace, extraordinary claims require extraordinary evidence. I don't think we're there yet, but it's exciting to consider and worth pursuing and concluding whether the tension is real and whether the size of the tension is as real as we're seeing today. And that's all.
Okay, thank you, Taylor. So it looks like we're starting to get some questions in the chat. So for those of you following along at home, drop questions in the YouTube chat for us if you want to ask Taylor something, and I will relay it here. Again, great talk, Taylor. I think I can just kick it off with a question of my own here. So you talk about measuring the brightnesses of these giant stars and how they are sort of a standard candle. Are there any differences among red giants, like their ages or their compositions, that you have to account for when making your measurements?
Yeah, so there's kind of a key class of these red giant stars that are standard candles. And what we do is by pointing into the outskirts of galaxies and targeting a special class of old, very old, just these stars, but very old, which means they're also very low mass, about the mass of the sun, these stars become standard candles. For other reasons that are a little too technical, so there's a consideration called metallicity, which is just the content of heavy atoms in a red giant star. And by moving to the outskirts, by targeting the outskirts of these galaxies with the Hubble telescope, we also control for that potential error that could bias a measurement using these red giant stars. So it's kind of a what's the word? A panacea for all the issues that could plague the red giant measurement by moving to the outskirts of galaxies, where with the Cepheids you'd point right to the middle, the bright disks that we all think of when we think of galaxies.
Cool. So in that case then, if the Cepheids are supposedly maybe easier in this sense, what sorts of, you talked about there possibly being problems with the Cepheid method of measurement. Could you briefly touch on what some of those might be?
Yeah, am I able to share my screen again?
Sure, yeah, go ahead.
Okay. Because that will help. So I showed this same slide for the red giants, right? So you can see the red giants. Oh, I can't see my mouse again, but on the bottom left, those are the red giants. And so what I've done here is I've zoomed in on the disk. So this is what I'm talking about when I talk about the outskirts and the middle of the galaxies. And if you see the red stars I've plotted here, it's by hand, but I did find the actual positions of Cepheids measured using Hubble and placed them on this image. And what you can see is they follow the spiral arms of these galaxies. And if you look to the very right, so I mentioned how the modern measurements of these stars have to be made in the infrared. So historically, they were all done in the optical, so visual, what we can see with our eyes. And as you move to redder wavelengths into the infrared, a class of stars called asymptotic giant branch stars. So these are kind of even younger, more massive versions of the red giants that we use in our measurements. And what they'll actually do is they're shrouded in these envelopes of dust, which retransmits light from optical wavelengths to infrared. And so these Cepheid variables actually get crowded. So that means a blend, so a star, so one of these asymptotic giant branch stars lands on top of a Cepheid or very near it beyond the resolution of the Hubble telescope. So this is where Webb is actually transformative. So if we're concerned that these asymptotic giant branch stars are biasing the flux measurements, so the measurements of the brightness of these Cepheids, then Webb can actually resolve them. You can measure the Cepheid free of those kind of biases due to one of these giant stars landing on top of the Cepheid.
Awesome. So maybe this is me being a little pessimistic then, but Webb has yet to launch, and we're holding out hope for this year. But if Webb doesn't launch soon for whatever reason, do you have an idea of what the other sorts of paths forward are for resolving the potential Hubble tension?
So the number one kind of route to resolving things right now, it has to be, so there's this tendency right now to push for further and further distances. And that's important because when you push the further distances using either the Cepheids or the tip of the red giant or the red giant stars, you increase the volume you probe, which is kind of how we measure the Hubble constant. We need to increase the volume to increase our measurements of another type of standard candle, which we use to actually probe hundreds of millions of light years out. And the problem is, if there's an accuracy issue, increasing the number of statistics at even worse, lower quality measurements. So the further you go out, your flux measurements will always get worse for the Cepheids, because basically, right, if I put my finger up close to the camera, it looks huge. If I take it away, the angular size of my finger shrinks. And the same thing happens to the galaxies we observe. And so what happens is this crowd and this blend issue of the giant stars landing on top of Cepheids becomes worse as you get to further distances. So you can think, I have two fingers. This is a Cepheid and a giant star. As it gets further away, my fingers start to look very close together. And this is kind of the heart of the issue for kind of pushing to further distances with the Cepheids right now. So the way to go is to figure out why the red giant method is disagreeing with the Cepheids. And there are some ideas thrown around, but in a paper I'll be putting out very soon, basically people have been trying to recalibrate the red giant method. But in a recent paper I'll be posting very soon, I show that these kind of attempts to recalibrate the method have been wrong. And so the problem must actually be in our measurements using the Hubble telescope. It's the only place where you can really find a problem with a divergence between the Cepheids and the red giants. So I guess, my route forward would be finding a way to make those two agree before going any further.
All right. I think we are running a little bit short on time now. So again, thanks, Taylor, for your talk. We're really glad that you joined us. And with that, I will hand it back to Steve to get us started on the trivia answers and wrapping up for the evening.
Thank you, Arvind. Let me just share my screen briefly. Oh. All right, you should see my screen here. We'll just go through the trivia answers real quickly and get the winner at the end. So the first question was, which astronomer said, "and yet it moves," being forced to recant? That was Galileo Galilei, pictured here on the right, facing the Inquisition. He's that very impressive figure right there. The second question, which standard for a planet did Pluto miss to be demoted? That was clearing the neighborhood of its orbit. Pluto failed that criteria and was relegated. In 79, Fred Hoyle actually claimed that the common cold had chemical similarities with interstellar dust and may have had interstellar origin. Urbain Le Verrier named his hypothetical planet Vulcan, a name it shares with the homeworld of Commander Spock from Star Trek. The alternative theory to dark matter, explaining galaxy rotation curves, etc., is modified Newtonian dynamics, known by its acronym MOND. Fred Hoyle, again in 49, argued the universe was in a steady state eternally, and he ridiculed what we now know as the Big Bang Theory, calling it a Big Bang and giving it its popular name today. The planet that was claimed to be discovered in 2012 around a nearby star, but then disproven in 2015, it was around Alpha Centauri b, which is one of the two stars in the Alpha Centauri system. The Danish astronomer Tycho Brahe lost his nose in a drunken sword duel with his cousin over who was a better mathematician. That certainly is a good way to lose your nose. And our bonus question for the night is: Moose died when it drank too much beer at a party and fell down a flight of stairs. So rest in peace, Tycho Brahe's pet moose. Number 9, this was a difficult one. William Herschel discovered Uranus in 81. It had actually been called all of those names except Minerva. A lot of people thought 34 Tauri, looks like a star's name and certainly wouldn't be a name for the planet Uranus, but it was actually noted in a star catalog some 50 years before its discovery, and it was labeled as 34 Tauri in that catalog. 34 Tauri has since been gone on to be used in science fiction as a generic name for an imaginary star. Question 10, Isaac Newton called his approach to calculus the method of fluxions and fluents, which is a pretty funny name for calculus, I think. Number 11, Hooke's law is the force by a spring, although Hooke was active in a wide variety of scientific disciplines. What used to be called Hubble's law is now also named after Georges Lemaitre, who was a Belgian monk. So it's now the Hubble-Lemaitre law, named after both of them jointly. This was another difficult one. The dwarf planet pictured here, the subject of the controversy, was actually Haumea. There was an argument between an American group and a Spanish group over who discovered it, and it went down in 2005. Number 14, Lord Kelvin suggested that the sun shone because meteors repeatedly impacted its surface, heating it up to iridescent temperatures. Now we know it's fusion in the core. And our last question, Giordano Bruno, his heretical beliefs included all of these opinions, which are now fairly straightforward scientific views. However, he did not believe a seventh planet orbits beyond Saturn. He did hold all these others, which is a little bit strange that he made totally random guesses and guessed correctly so many times. The winner of tonight's trivia was the team Anti-Darker Matter. Congratulations. It was a very close runner-up with the team The Empire Did Nothing Wrong, which, of course, that team name is ludicrous. The Empire destroyed planets, and that's silly. So congratulations to our winner. We'll get in touch, and thank you, everyone, for playing.
Thanks, Steve. I think it would be nice to point out that not only did Tycho Brahe's moose die from drinking too much, I think Tycho himself also died from drinking too much beer.
The story goes that he partied a little too hard one night and had an unfortunate accident. Yes.
Wonderful. Yeah, congratulations to the winner. Thanks, people, for playing. And thank you, everybody, for tuning in. Thanks, Jack and Taylor, for some great talks. We will be back again next month. Nothing is set in stone yet, so we will reach out to everybody via Twitter, Facebook, and email to let you all know what's happening. Again, thanks for joining.
Thank you for having me.
Okay, we are no longer streaming.